Hello and welcome everyone to WFO's webinar. My name is Ilya and I'm the Senior Business Development Manager at World Forum Offshore Wind. Today's topic is on offshore wind technology updates, and it's my great pleasure to welcome a panel of excellent speakers today. We have Bethany White, a Senior Associate Offshore Wind, and Christina Starost, Associate Offshore Wind at Carbon Trust. We also happy to have Lars Samuelson, as Strategic Marketing Manager at American Bureau of Shipping. And we have Amir Izzat Parast, Manager of New Technology Development at Scitech. And before we jump into their presentations, let me tell you just a few things about WFO. The organization was founded about 5 years ago, and we are the leading global business platform for the offshore wind industry. By connecting and supporting our members, WFO is helping to make offshore wind one of the world's leading source of renewable energy. Our members represent the complete offshore wind value chain with offices in Hamburg, Tokyo, Taipei, and New York. And in terms of our activities, it's very straightforward as we focus on 3 things. We provide advisory services for offshore wind around the world. We inform about offshore wind. We are publishing reports, facilitating a number of working groups, especially in floating offshore wind, hydrogen, and conflict resolution. And we organize events for connecting the global offshore wind community. And just less than 1 month, we're going to have our next event. That's going to be our second WFO Asia Pacific Summit. Please feel free to register for the event, or if you have any question, do not hesitate to contact me. And in terms of our members, we have over 120 global moments at the moment, and they represent the entire value chain and we have companies from North America, Europe, Asia, Middle East, and Oceania. And if you're not a member, please feel free to join us, and you will be a part of this global network. Again, feel free to send an email to myself or our Managing Director, Gunnar Hersik. And now just a couple of words about the structure of this webinar, which is very simple. During the first half, or maybe a bit more than half, we'll have presenters on the topic for today's webinar. And after that, we'll have Q&A session. So for that, please feel free to use your chat function on the control panel on your right-hand side. And without any further ado, our first speaker for today would be Christina. Christina, over to you.
Thank you, Ilya. Thanks everyone for giving us the opportunity to present today at WFO's webinar on offshore wind technology challenges. My colleague Bethany White and I, Christina Starost, are going to give you a bit of an overview of the ongoing R&D initiatives that are currently ongoing at the Carbon Trust. While the Carbon Trust obviously has a wide offering, we particularly focus on offshore wind R&D research, driving offshore wind development internationally. And in our offshore wind programs, we particularly focus on collaborative developer-led research, for which we set up 5 different programs. We have the Offshore Wind Accelerator, our flagship R&D program that predominantly focused on fixed bottom offshore wind, which was set up in 2008 and has helped to significantly drive down the cost of offshore wind over the last decade. Then we also have a program that focuses on floating wind, the floating wind JIP. With new technologies emerging on the floating side, it is important to bring the industry together to kind of have a similar development as in the fixed bottom sector. We have another program, the ORGIP program, that focuses on reducing consenting and environmental risks for offshore projects, with non-price criteria becoming more and more important, and the seabed getting busier and busier. It's important to pool knowledge and get together on the subject matter as well. And then the integrator program, where we focus on the interplay between offshore wind, existing infrastructure, and other technologies and just like really facilitate like a more holistic approach to the entire network when it comes to taking in more and more renewable energy. And finally, our latest initiative, the Sustainability JIP, was set up in 2023. The industry is growing, and obviously we also have to make sure that we grow the sector in a responsible way. We have to decarbonize where we can. So the program specifically focuses on how offshore wind farm developments can decrease their carbon footprint, and we also aim to support developers in achieving net zero targets and making their their projects less impactful from a carbon perspective. So on the right hand side you can see the companies that we work with, but also government bodies. There are lots of developers, stakeholders that we work with. These are just a few of them. We have a broad network and are really able to leverage a lot of expertise across the industry in our projects. So I don't want to dwell on this too much further, but go into our first project that I'm going to present you today. That was set under the Offshore Wind Accelerator. It's the Donis project. Donis stands for design of offshore monopiles, including seismic interaction with soil. It specifically focuses on emerging markets where we find seismic activity and where seismic activity impacts the structure of offshore wind farms, the structure of turbines. The regions are getting more and more important. Countries want to unlock their potential and realize very ambitious climate targets. But in order for them to do so, we need to make sure that we establish a design for offshore wind turbine support structures that takes these seismic interactions into account and really close knowledge gaps on the seismic response of the turbines towards the impact during earthquakes or tsunamis as well. Also identify, evaluate more how monopile design drivers are impacted. We want to take into consideration what we expect in terms of pore pressure effects, and just develop practical tools that could be used by the industry, by developers for their design, site design in new markets. So it really was the motivation to develop a de-risked, more resilient monopile design. So the project is kind of split between a publicly funded part where we were able to leverage funding from the Dutch Research Council, NWO, through the technology, open technology program, and a privately funded part that was driven by the Carbon Trust, where we leveraged funding from the industry partners that are involved. We were able to bring together a quite high profile research team. On the right hand side you can see the project coordination, and lead is taken by TU Delft. We work with Professor Kementzidis and also Professor Metrikin, which are experts in the fields at ETH Zurich. We work with Professor Anastasopoulos on the experimental testing side. They were very forthcoming in providing their centrifuge for large-scale shaking tests. We work with NGI and NTNU, Federico Pisano and Professor Kanya, both experts in the field, and then kind of bridging over to industry partners as well. Siemens Gamesa Renewable Energy is playing a significant role in driving the project as a wind turbine OEM and really providing the insights from the OEM's perspective on seismic impact on the turbine design, and then also making sure that we develop tools and kit that can be incorporated into softwares that are provided by Plaxis and Bentley, for example, so have their input as well. So quite a lot of knowledge, and the project is structured in the sense we've referred to it as COFI modeling approach. The first work package is focusing on the constitutive modeling, predominantly performed by TU Delft and a geotechnical consultant, Great Geo. And the physical modeling in work package 2 is conducted by ETH Zurich. As I mentioned before, they have just inaugurated their large centrifuge last year, and we are able to perform large-scale shaking tests there. Then in work package 3, consolidating FE modeling, near and far field, and in work package 4, the engineering modeling itself. So we really try to realize a lot of benefits here. We want to reduce uncertainty, mitigate risk, improve knowledge and understanding of the impact of seismic loading on offshore structures, but also, yeah, in terms of commercial benefits, it's always important for the Carbon Trust to keep that developer lens and business case in mind, really develop advanced methodologies for monopile design, avoid over-conservatism that can be very costly when you look at multi-gigawatt developments, and also reduce liabilities when it comes to actual incidents in the water. So we want to develop industry best practice tools that can be practically applied, and therefore we also engage certification bodies in the project. We work with Bureau Veritas, DNV, and NCREE, the Taiwanese Research Institute, that bring their unique market experience and try our best in this way to increase the acceptance of certifiers as well and support the dissemination of the results across APAC and also the west coast of the US. As I mentioned before, there is public and private funding leveraged, and the project will run over 4 years. It has kicked off in January 2023, so until 2027. And yeah, we expect the first results to be published in 2 years' time. Some of it will be shared with the wider industry, but most of it will remain confidential for the time being. But yeah, we're really excited to see what the outputs of this research project will be. They will be very relevant, and excited for that to properly kick off. I'm going to hand over to Bethany now to talk about another initiative that we are currently realizing.
Okay, so we'll now move on to discussing a key challenge around cables. So this is related to soil thermal properties, as you can see from the title. So in relation to inter-array cable and export cable design, thermal properties of soil are critical to making those designs, but there's a lack of clear guidance around conducting tests and interpreting results of tests, which is often leading to conservative cable design choices, and in return that leads to potential cost overruns for projects. So in order to address this challenge area, within the Offshore Wind Accelerator's Cables Technical Working Group, we recently completed a project called Soil Thermal Properties, which is looking to address this uncertainty. So the way we went about this was to investigate the methodologies for measuring thermal properties of soils. So looking at IEC standards and also fundamental physical laws. We also looked at enabling increased accuracy of measurements and assessing implications for subsea cable design. You can see the project was delivered by CAFI, ITP Energized, and University of Southampton. And yeah, this was done in collaboration with the 9 offshore wind developers in the OWA, and was conducted over 3 years, sorry. So you can see on the slide the outcomes of the project. So in particular, we've got the so an investigation strategy for laboratory and in situ testing of soil thermal properties. We also provided an understanding of the potential changes of thermal properties in response to installation effects and the implications of these for cable design and operation. So this diagram on the right-hand side is showing so the different parameters that can affect the cable design, and then we've got some factors along the bottom that can be adjusted to reflect these. Okay, so where did we go up to? So yeah, so we established a basis for determining appropriate characteristic values to be used in the design, and we also recommended improvements to the measurement techniques and interpretation of results for offshore use. So there is a report on our website which is linked in the slides here, which will be sent around afterwards. So yeah, if you'd like to know more detail about any of those options, any of those outputs, then you can click on that report and have a look. It's on our website. But yeah, as a result, the industry can potentially save tens of millions of pounds of capital expenditure and reduce operational costs, which should pave the way for more efficient and sustainable offshore wind projects in future. And yeah, that's our presentation. We're happy to take any questions in the chat afterwards.
That's great. Thank you very much. And now we're going to the next presenter for today, Amir. Amir, the virtual floor is yours.
Thanks, Ilya, for the invitation. This is my first time joining WFO webinar, so I'm a rookie. And do you guys see my screen?
Yes.
All right. My name is Amir Zatparas, and I'm the manager of new technology development with Sofec. But my background in the past maybe 12, 13 years, I've been a mooring designer and worked on different phases of the project. So what I'm going to talk about is how we as mooring designers and EPC contractors look at the challenges of the mooring for the floating wind farm. And the focus is going to be on the farm size. And I'm going to give a couple of challenges that we face on some of the studies that we have done. Very quick about the introduction of Sofec. We are an EPC contractor for the mooring systems for different type of floaters, but our core has been external turret, internal turrets, and spread moors and tower yokes, and COM and some offloading or like offloading systems for oil and gas projects. And a little bit about our involvement in floating wind. We have been involved in different levels of floating wind for the past 12 years. Our first actually involvement on a very interesting concept that we did with our parent company, Modec, but unfortunately it wasn't a successful concept, but it was a very interesting and a lot of learnings there. And since then, we have worked on different concepts. For obvious reasons, we have worked on pilot projects for our single point mooring designs, and we have our own concept as well. But since 2021, with our parent company Modec, we have focused on development of the semi and TLP designs, and also done quite a few studies for mooring analysis at different phases on pilot programs all the way to the farm level as a mooring designer. So that's where our focus is, to stay with our core experience of a mooring supplier for the floating platforms. Before I start getting a little bit maybe negative and talk about challenges, I have to start with this, that this is a very exciting time to be a mooring engineer. And I say that as someone that has been part of this industry for the past 10, 15 years. What was asked from us mooring engineers during, like in most of the oil and gas projects, it was a robust design, no technology, new technology, everything was standard, and you tend to just go through the motions and design a system that is very robust and very, let's say, just fit the purpose of the project. But now you see the shift, and it's a good shift for a mooring engineer, and especially if you're in the new technology development, that we actually have a very large portion of the cost and also the scope of a floating wind project, and that has opened up the door for a lot of innovative designs. Like you guys, if you just search online, you see like V-shaped mooring, shared legs that it was never studied or looked at, and there are new materials being studied. I think the last time we actually introduced a permanent mooring component to floating platforms in oil and gas was 1995, when Petrobras started using polyester. But now we're talking about nylon as a long-term mooring, load reduction devices. There are new pile designs coming up, and they all have some interesting merits. There are new installation philosophies. We come with a background that everything has to be fine-tuned, everything has to be controlled in the offshore, but now we're coming with philosophies that can we even just have two legs of the system tension, and the rest is just what we call like a direct connect. We are challenging the common designs. Like if you look at the oil and gas, we never used taut legs in shallow water, but now it's even becoming common in the oil and gas sector. We see like long polyester or nylon segments in the water. In shallow water designs, we are challenging the requirements. We typically had the synthetic ropes at somewhere around like 100 meters of water depth. Most of them are used for deep water systems anyways, to protect them against marine growth and all that. But now you see like designs with synthetic ropes directly connected to the top that gives some advantages to the design and also the installation. We now, after like quite some time, we are getting a little bit more relaxed about evaluating the risk and cost balance. As I mentioned, like the idea of a mooring engineer was always looking at a robust design, but now we can actually look at non-redundant designs or versus like redundant designs. And we are also looking at very optimized and highly utilized design, like shared anchors is one of the major things that has been done in the past. And I have to actually give credit to the companies that have used their pilot programs like PPI, BWI, Dole, Equinor. They have used their pilot programs to study some of these and actually do like a full-scale test, and they're helping the industry quite a bit. Something else that also comes with a little bit of maybe challenge is that now the mooring system it has quite a significant impact on the performance of the floating wind itself, or the floater itself. So you need to have a fully coupled analysis. That has been a tradition in oil and gas, that the mooring provides the loads or the interface loads to the floater, and the interactions are a little bit disconnected from there, or at least like the interfaces are quite simplified. But now we are getting to a point that everything has to be done together. The mooring, like I think if you look at some of the spar designs, it's very interesting that the mooring system design can help with the yaw stability, or also with the semi design as well. By the way, I put everything here. It doesn't mean that I'm advocating for all of this. We have studied a lot of this, but this is just a great time to look at new technology in the mooring. And like most people, I think when we started looking at floating wind and the mooring design, we focused on the challenges with the individual floater. That was kind of natural. We started working on the concepts and the pilots. And the biggest change for us was the wind load modeling compared to what we had on let's say, oil and gas platforms. There are still a lot of uncertainties about the wind load. We still have the challenges on how to model the wind turbine correctly at the early stages of the design, but that has been the focus, and I'm not going to get into that a lot. There are a large number of load cases, and a lot of them are new, and something that we actually learned and relearned again is that there are a lot of or multiple governing conditions. Coming from oil and gas, you usually start with extreme analysis, and then it works out that the other cases are not as critical. But you can actually see on floating wind, there are going to be multiple operational or extreme cases that could actually govern the design, and you cannot relax, let's say, the load case or load matrix too much. And what we have actually learned is that fatigue could be the governing case for a lot of our designs, and especially like if you're using like a chain segment that does have its issues with fatigue. These are very dynamic systems, relatively small, and we are looking at harsh environments. Obviously, you're looking at places with good wind, which also comes with good wave, and that is also causing a lot of challenges. A lot of the sites that we are looking at are shallow waters, and for any mooring engineer knows that the shallow water effects, and this is nonlinear behavior of the wave, the wave kinematics are different, and also the geometrical view of the system is going to be very constraining. Like we actually saw like quite a lot of snap type loading in some of the earlier designs that we evaluated, and since then are moving into like having softer systems. Like I put like a picture here just for you, like how like a taut mooring system or semi-taut design in the shallow water would look like. That also gives you more compliant and also try to minimize the snap loading. But for the, let's say, past year or so, we have been asked, or we have been participated in proposals or pre-feed or studies for farm level mooring systems. And something that was quite like at the start, like we saw that, and it was a challenge that we had to tackle, was the water depth variation. And it sounds simple. Obviously, like you're looking at sites that are closer to the shoreline, you still are in the slope zone of the soil, or like in the slope part of the ocean. Typical sites that we have looked at, the water depth variation is somewhere between 75 to 250 meter depth, but we also have looked at extreme cases that you could be somewhere between 100 to 500 meter on a larger wind farm. And the typical approach, and part of it is the way the scope was defined, and part of it the way that we were a little bit naive perhaps, that you start to design an average water depth. And for a mooring engineer knows that this doesn't mean that it's a quick thing, so you actually spend a lot of time to define, like, is it going to be a redundant, non-redundant design, a lot of iterations on the design types. Is it going to be catenary design, or is it going to be like a taut or semi-taut? You go through all the load cases, and this is a large scope by itself. You develop an optimized solution, and then the next step is do sensitivity for the range of water depth. I just put an example here. This is actually a study that we did, and I'll say that the focus of this was not really standardization. This is a water depth of about like 75 meters to about 200, which doesn't really seem too much. We started at an average water depth of about 100 meters. We optimize, or let's say a relatively optimized solution, that's what you see on the top. It's a catenary design. It's very traditional design that has been used also in floating wind industry quite often, and with a, let's say, a synthetic rope for the top connection and a chain segment in the middle and a heavy chain and also bottom chain. This design was relatively mature. Then we started looking at the shallower water of 75 meter. Obviously, we value the standardization of the components, but as soon as we looked at it, we realized that we won't be able to use the same component sizes. And then when you go to the deeper water, you actually see that you could optimize the system quite a bit. This study's focus was on optimization actually for different water depths. It's not a real case, or it's not something that we would do for a real life farm, because you tend to give more balance to standardization of the components to be able to fabricate. But that also means that you are going to actually be not very optimized on some of these water depths. So the challenge that we have right now, and we see that pretty much like on every study that we have done so far, and also like even the more serious RFQ process, that what is the balance between standardization and optimization? Do you design, let's say, for the shallowest water that is going to be the more critical, and then apply the same components over the entire range? Or do you come with a balance, or do we cut the systems or like the field into, let's say, certain water depths? That's still like a debate. And also, what is the resolution, the right resolution of water depth for analysis? Because you are going to see, like in the next slide, that some of these fields, they have really sharp drop of the slope and the depth, and how do you actually manage that when you're actually looking at different water depths? One of the bigger challenges that we have, and this is related to what I mentioned before, there are going to be a lot of unique cases in the field, and that you're going to be on the slope and you're going to have different water depths, that mooring legs are going to be sitting at different water depths. And how many of those unique cases do you need to consider to A, first of all, like get class certification or class design approval, and B, make sure that you have looked at all the combinations that could impact the floater and also the turbine design. So that's the balance that is very interesting. Just a side note, like this is kind of like, it's very known for the mooring people, but I see that it's probably not as much known, that there's an idea that maybe when you go to the deeper water depth, the mooring system becomes more expensive. But to some extent, that is not the case. Usually the shallow water designs are the more expensive and more challenging designs because of the geometry and the nonlinear effects of the stiffness of the mooring system. Just look at these three designs that are done for the same floaters, same environment, same everything, input the same, and we have designed it a little bit differently. And you could see just from the component arrangement and also the sizes that the deeper water, that's about like 200 meters, you could have a much more optimized and cost-effective design. Another major challenge that we have, that we are still figuring that out, and I think we are not unique in that sense, that the site size and variability in the soil characteristics is quite challenging and very difficult to manage, especially when you're working at the early stages of the design. If you look at at these kind of water depths, let's say 250 meter of water depth, a typical FPSO has a radius, pile radius or mooring radius about 1 kilometer. That's the area that you need to consider about your geotechnical. And we still see variability. We still see impact in the design of the pile between different clusters, especially if you're on the slope and you can have different composition of the soil. You have to consider exclusion zones, which could impact your mooring arrangement, and we have more flexibility there. And now, if you look at the typical size of a 750 megawatt wind farm, that's about 25 floaters. You're looking at about 250 kilometers square. So that's about 12 kilometer by 12 kilometer area that all these challenges are going to come with it. I just put an example here. This is a very exaggerated example on the top that you see from the shoreline all the way to somewhere around where the site starts and all the way to the depth that it's considered. You can actually see that the soil starts with having a little bit of mud on the top, a little bit of sand layer, and then that sand layer goes away and it becomes all rock. And you're going to see a very sharp drop in the slope as well. So when you look at this, what is going to be the scope of geophysical and geotechnical survey? Obviously, the entire site needs to be done under a geophysical survey, but how many bores do we need and how much variability we have is still quite unknown. And how many pile designs are we going to look at? Right now, we see a lot of standardizations that one pile size is going to be used for the entire field, but I feel it is a little bit, it's a hopeful assumption that we are going to be able to do that. Even on the oil and gas, we can actually have piles in different sectors, and within the smaller radius that we are talking about, they're going to have different designs. And can we even use the same pile type in the entire field? A field like this, you might say that I can use drag anchors on this side, and then you hit the rock, and then what do you do with this side? This is going to be a drilled pile and grouting, and there might be different characteristics that you won't be able to use the same pile design for the entire field. And how do we deal with the exclusion zones? I think it looks simple when you actually look at it and say, well, we can actually, but when you actually look at the entire arrangement of the field, moving the floaters become very constrained. Also, changing the azimuth angles means that you're going to have a lot more unique designs as well. And it just complicates the whole design process and number of unique cases that you have to look at. Something else that we have discussed with some of the developers, that how much flexibility do we have on the site arrangement? A lot of these sites, because of their nature being close to the shore, you have a very directional environment, wind coming from certain directions with an angle, the current or waves are coming from different angles. And from mooring design perspective, you can optimize it. But that doesn't mean on the farm level, you can actually have that flexibility. The farm shape is not exactly aligned with your arrangement. Also, you're going to be interfering with all the exclusion zones and other cable passing. So there's going to be quite a lot of constraints. That means that you are not going to be fully optimized. Something that we have actually tried, and I think on many occasions we have failed, the whole idea of pile sharing is quite intriguing. It's very interesting. It makes a lot of sense. But when you consider all the slope restrictions and all the design performance requirements and everything, it seems a little bit constraining. And is it really realistic for a typical site to be able to manage the radiuses and the lengths and arrangement all perfectly, that you get a honeycomb shape that we typically see? On my final note, and that is a little bit of what I would call it a little bit of pet peeve. We get invited into studies. We also look at studies that are done by others. Usually, when you start a field development, there's a lot of focus on the floater design. That's where the majority of the inputs are available. The mooring becomes an afterthought, or typically what happens is that you actually go with a limited information on the geotechnical and the site conditions. So you make a lot of assumptions. And there's this phrase that drives me at least crazy, that we say that this issue or this challenge or this data is lacking, so we actually have to do it in the detailed design. And then when you look at the detailed design, I did not touch anything on the supply chain issues, on the component supply, on the shipping and everything. Though that is really like where the focus needs to be. You have a design that is relatively mature and move on into the execution. But we see that sometimes I call it like a bodybuilder that forgot the leg day. So the floater itself is very well developed and the design is relatively mature, but the mooring part, because of the, let's say, the uniqueness of each side, is kind of like a little bit, it's not as mature enough. That was my last slide. Thanks for listening, and I'm happy to get your comments.
Okay, perfect. Thank you very much, Amir, for this very great and insightful presentation. And now we have the final speaker for today, Lars. The virtual floor is yours.
Thank you. So a little bit short of me, naval architect, been doing offshore since last century. So I was through, Amir talked about all the innovations. Oil and gas had the same phase of new innovations and how to address things that were not really addressed in current standards back then. So this is really interesting to go through the second phase now for renewable wind. I'm also the chairman or co-chair of the IEC-3-2, and the FTIS, which is the last stage, will go out here in June. So hopefully we will have the bigger and better version of the IEC standard for floating wind out towards the fall, end of this year. Very short about ABS. Most of you probably know us, but we are non-for-profit, basically here to serve the industry, both the designers as well as the finance and insurance industry, to provide a baseline through design, construction, operation, and maintenance. This is the last slide about ABS. Just want to show what we have done in real life. So these are all installed units, more or less 80 megawatt of floating wind, going back to 2012 or 2011 when the WindFloat 1 was installed offshore Portugal. Then we have the WindFloat Atlantic, 3 units, 8.4 megawatt, also of Portugal, and the Kincardine, that was 5 units, 9.6 megawatts, offshore Scotland. And it had been really fun to be through the entire development stage. Like the first little WindFloat, there were not even any rules in, so we had to take more of a goal-based approach, although it wasn't defined, but it worked so well that it could be reused in Scotland 6 years later. So this is basically how to address the design of something early on in the stage. And as Amir said, it's important to address all parts at an early stage. And a good tool to do that is hazards, workshops, etc., to come up with a risk register so you understand the consequences and the mitigations that are needed. For many of these new concepts that we've been working on, and we've been working on quite a few, we have done this path. We're trying to go down the engineering operation route as well as the risk assessment route to just reduce the uncertainties to an acceptable level at the typical stage. I'm trying to speed up here because I see we're running a little bit out of time. Just want to mention we have a guide for floating wind turbine, basically addressing everything below the tower flange. And we have a guidance note just updated to include guidance on integrated load analysis. And those are the key and the main difference between what we are commonly used to from oil and gas into wind. So this is really what I want to talk about, the goal-based approach. Because we are trying to drive a new industry, we need to drive down cost, and we don't want to stop innovations just to shoehorn them in to the current prescriptive rules, right? So this is basically the structured process, and on how to go along. and this is a quicker one, and we take less risk due to the predefined goal and functional requirements. And another thing we haven't spoken about here is, in the end, you will need insurance and you will need bankability, and it doesn't hurt to engage them early on in the process either, to increase their confidence level. For example, what we did for the Windfloat 1, we were the independent third party, but the EDP, which was the Portuguese electrical company, were heavily involved in all of these risk workshops, hazards, etc., to understand the risk they were taking and increase their comfort level. So the goals, as you see, the high level objective is the goals. We focus on safety, environment, security, and bankability is sort of a result of those three, I would say. Then functional requirements and what is addressed already and what is applicable from the prescriptive rules, for example, from that ABS guide I mentioned, or from IEC-3-2. So we narrow down, we know the path we're going, and we can focus on the unknowns. And looking at the necessity of this, so this Quest database, right now we have 145 concepts, and per their definition, they find 65 of them being not mature, 15 of front runners, and then we have 4 proven floating foundations. I think we all know which they are. And as I said, for the items not addressed by the prescriptive rules, use a goal-based approach, address it early on, no matter how small the piece is, because no chain is stronger than the weakest link. So you need to have a good understanding of where the risks are and what are the mitigations early on in the project. And these tools I talked about earlier are good tools to utilize in this process. How about that for a speeded up presentation? Now we have 15 minutes for questions.
Okay, perfect. Sounds great. Thank you. So yes, now we actually have time for questions. And feel free to use the chat function on your right-hand side and just insert your questions there. So to begin with, I have a general question to all of our great speakers today. Maybe just in your own words, with your expertise, if you can just share what are the most pressing technological challenges in the offshore wind industry from your perspective, maybe from the country you're based. You can just mention a couple of them or just one. It's really up to you. And I think we can start with Bethany and Christina from Carbon Trust, and then with comments from Amir, and then Lars.
Yeah. Beth, do you want to go ahead? Do you want to say something first?
Yeah, I can go first. Yeah, so I suppose I'll come at it from a cables perspective, as that's where a lot of the projects I work on are in that area. I think a key thing is the transition to 132 kV to facilitate larger wind turbines. So yeah, it's going to be around getting those cables procured, understanding what the requirements will be for those cables, and yeah, the supply chain kind of pulling together to facilitate the move to 132. Yeah, I think that's probably my key thing. There's lots in the cable space to talk about, but yeah, just one thing for me to highlight. Christina.
Yeah, I think with kind of like the focus that we touched on with the Donis's project in relation to foundations, the new markets that are currently opening, they're very exciting, but obviously we incur very different soil conditions, very different parameters to account for in the design of monopile foundations, and also impact on other foundation types, obviously. So I really think that a lot of research will need to go into this to accurately reflect these effects in design tools to avoid any incidents, losses during installation or like over the lifetime of an offshore wind farm. So I think, yeah, there's lots to watch out for, and I'm sure a lot of research will be conducted to address the challenges.
Perfect. Thank you, Bethany and Christina. Amir?
And I'll also focus on what I know. Like there are obviously like different technology developments beyond like floater and let's say the turbine and mooring. But I think this is kind of like what we have discussed as part of the JIPs that we are involved with DNV and others, that we are still looking at the wind load as what we have been doing on the FPSO side. The uncertainty on the wind load is still quite challenging to capture in the design codes. The fact that OIMs get involved in the project a little bit later, and that's when you get, let's say, their actual control system, their actual loads, it's quite challenging. And I think we have to find a way that we can manage that risk and uncertainty within the project, and also be able, like, pretty much like everything that Lars mentioned, like all these projects have instrumentations, they're measuring the loads, they're measuring the responses. I hope that at some point those start getting published and studied, that you can actually see the actual performance of these systems, not from, let's say, power generation only, but the actual responses that you can feed back into the design stage. And on the mooring specifically, like there is quite a lot of actions that are happening on the qualification of nylon, and for good reasons. Nylon gives you a lot of advantages on the compliance and the stiffness of it. So that's going to be the focus, at least for us as well, for the next few years.
Perfect. Thank you very much, Amir. Lars?
Yeah, I would, since I spoke so short, I'll bring up three of them. I think turbine size is a big mystery right now. We don't know if it will continue to gallop up 20, 25, for example. You hear rumors about them. So from a design perspective, what are the floater we should design to? And along with that comes the need for a prototype. This costs a lot, and it delays the project a long time if a new concept will need a prototype or not. And what are the alternatives? Would it be more detailed model test? What should the size be of a prototype, for example? And I believe Equinor went out and said that if you're going to do a 3 columns semi, we know how they behave, we will not need a turbine, a prototype. So that's a big uncertainty, and that's something that very often is driven by insurance and banks, as I said, because they tend to be forgotten in these discussions, because we are all engineers and technology driven, but in the end they need to be bankable and insurable. And the third one is the supply chain. So I saw Amir had 180 millimeter chain already, and I assume that was for a 15 megawatt. If we're now trying a 25 megawatt, what happened with the chain size? Considering, yeah, you're shaking your head. So you will either need more inlines or new chain factories. So those are the three of the items: the turbine size, the need for prototype, and the supply chain, that I think need to be addressed and should be addressed early on in a project, not after the design have started or the feed has started. Yep.
Okay, perfect. Thank you very much. Then the second question, we have received a few questions regarding floating, and just if to sum up, so how could floating offshore wind development could benefit from the technological advancements, and especially maybe in the deep waters? So any thoughts on that? Maybe we can start with Amir this time, then Lars, and then Bethany and Christine.
I think what the trend that you see, that people are using new technology and new ideas in the pilot programs and maybe pre-commercial limited number of floater type approach is very encouraging, and I think we should encourage that more. when you say deep water, like at least like from what we see from floater side, from mooring side, deeper water does not really worry us. I would probably think that the cable is going to be the bigger challenge, and how you manage that cable. Like it's going to be a bigger issue, and probably a lot of focus would go to. And deeper water for mooring system does not really mean that you're going to have a lot of challenges with the design, and you would need new technology, like at least from our side. Unless you suddenly have to go with sites that are not very pile friendly, I would say, like very rocky, and you're going to have challenges. But at least deeper water does not necessarily mean that you're going to have more challenges, except for the cable that could have some issues.
Okay, thank you very much, Amir. So we can go to Bethany and Christina.
Yeah, I think from my perspective, at least, yeah, the experience that I collected in many markets at the moment, we like find ourselves in this pre-commercialized stage. Like we don't have a prototype to take forward and manufacture at a large scale. And a lot of countries are releasing very ambitious floating wind targets, but I feel like we really need to like catch up and make sure that we have technology available, that we have technology that we could can produce at a large scale and get into the water as soon as possible. I would agree with Amir. I think from a technological perspective, it won't be the depth of the water is not the challenge here, but more like the scale and like rolling out technology in a way that could be like installed as soon as possible to realize the targets that are set.
Perfect, great, thank you.
And yeah, just to add from my perspective, and I suppose from a project I'm working on at the moment, it's around load reduction devices and commercializing them at a on commercial scale turbines. So yeah, one of the projects we have going on at the moment, the Lord project, is looking at doing a commercial scale demonstration of a load reduction device, the TFI C-spring. So I think alongside that, and we're also planning to do a roadmap to commercialization, just trying to speed up the development of all of the technology needed to roll these out. So yeah, similar to what Christina said, there is a lot of development needed in the floating wind space in general. So yeah, I'll hand over to Lars.
Then you're on mute. No. Yeah, you can just unmute yourself on the pictogram. No, that's unfortunately no sound from your side. Usually, yeah, there's a pictogram to click. So we only have 2 minutes left. There is a question, and I guess that will be the last one. And is important to consider the technological developments on the assembly onshore areas. What can be the first thoughts regarding the tech development in ports? So I guess, yeah, any volunteers regarding the port infrastructure and technological developments, please, you have like 30 seconds.
I think I can go first. Like, yeah, like that is going to be the bottleneck for a lot of this industrialization work that even our parent company has looked at, that how you're going to, it is maybe on the shipyard side or the fab yard side, you can think about the industrialization and how these modules are going to be put together. There's quite a lot of effort, not just by us, by everyone, on the modularization of the floaters and how the fabrication is going to happen. And this has happened in the offshore industry in the past, that there's some track record of it. But when it gets to the ports and you now have to streamline all this process, getting to the port, get the turbine integrated, there's quite a lot of unknowns and also challenges with that does not go well with the whole idea of like a serial fabrication and getting things into the water on a kind of like a continuous manner. I think a lot of it is perhaps like investments in the ports, but as you mentioned, there's going to be a lot of technology advancements, and how can we maybe start thinking about installing these turbines a little bit differently. So we can help with the pause. There are discussions about like having segments of the like crawlers type installation of the wind turbine that could help with the process, that you can do it maybe not in a port or a quayside, but or you don't need the type of cranes you would need. But yeah, that's going to be, I think a lot of investment needs to be done there.
Still have a few questions, but because of the time, this is the end of the webinar, unfortunately, but we'll have more webinars in the future. Please check out our website for new webinars. They will be happy to continue the conversations. Thank you very much, Christina, Beth, Lars, and Amir, for your time today, for your wonderful presentations, and thank you very much for attending this session. So enjoy the rest of the day. Bye-bye.
Thanks, everyone.
Thanks, everyone.